And now we're going to look at probabilities for dependent events. Dependent events are where the occurrence of one affects the probability of the other. Here's kind of the formal definition. A and B are two dependent events if the occurrence of one of them has an effect on the probability of the other. And now if we were to look at the probabilities of the two events occurring together, we can't just multiply the individual probabilities because one of them is affected by the first one. The second one might be affected by the first one's occurrence. And so what we actually have to do is multiply the probability of the first one by the probability of the second one, given that the first one has already occurred. This notation with that vertical bar is a notation that represents the first event, the one before the bar, happening given that the second one, the other one on the other side of the bar, has already occurred. Okay, so P/A or P given A is the probability of B given that A has already occurred. All right, so here's an example. I do a lot of examples with cards because it kind of makes sense. But here it says, find the probability of getting 2 face cards dealt in a hand of Texas Hold'em poker. Okay, now 2 face cards. Basically, the first card dealt would have to be a face card, so there's a probability for that. And then the second card dealt would also have to be a face card, and there's a probability for that. 2 separate probabilities. Now, there are 12 face cards in the deck, right? There's a Jack, Queen, King, that's 3 for each suit of 4. 3 times 4 is 12. Okay, so there are 12 face cards in a 52 card deck. All right, and Texas Hold'em poker, you just get 2 cards dealt in your hand, and then there's other shared cards, which I'm not considering. I'm just considering the ones in your hand. Okay, so 12 face cards in a 52 card deck. Well, if the first card dealt to you, the probability that it is a face card is 12 out of 52. Okay, so the probability of the first one being a face card is 12 out of 52. Okay, now the second one, in order for this probability to hold true, the second one has to be a face card, assuming the first one was. If the first one isn't a face card, then this doesn't even apply. Okay, so we have to assume the first one's a face card. So what we do then is you calculate the probability with that first card, the face card, dealt out of the deck. So let's say I got a Queen of Hearts as my first card, then I already know there's 1 face card dealt out. Okay, so the size of the deck is smaller, right? There's 51 cards now instead of 52, and the number of face cards is fewer. There's 11 instead of 12. All right, left over in the deck. And so, my marker, there it is. So the probability of a face card, given that a face card already occurred, is going to be 11 out of 51. Okay, because you've removed 1 face card from the deck essentially. And so now the probability that both the first and the second are face cards, okay, so the probability of face and face is going to be the probability of the first one being a face card multiplied by the probability that the second one is a face card, given that the first one was a face card. If these were independent events, in other words, if I could replace the original card back into the deck and it wouldn't change the probability of the second card, then I would just multiply the 1250 seconds times 1250 seconds. It'd be the same probability on both. That would be an independent event. But this is dependent because the second probability, the second face card, is dependent upon the first one already being a face card. You pulled it out of the deck. Okay, so it changes the counts. And so what we would end up with is 12 out of 52. Boy, that's terrible looking 5. 12 out of 52 multiplied by 11 out of 51. Okay, and so this combination will give me the final probability of getting 2 face cards. Okay, now I don't have my calculator, I gotta grab that. There it is. Okay, and so I'm not going to try to take any shortcuts on this one. We're just going to go 12 times 11. That's 130. I need 132. Good grief. That's 132 on top. 52 times 51, I don't know. Although I could get it pretty quickly. It's 2652. And so if I wanted to reduce that, I probably could. 132 divided by 2652. Math frac. That is 11 out of. Is 12 going to 52? No. Oh, but it does go into the combination. That's kind of interesting. Okay, so it ends up being 11 out of 121 or 221 in reduced form. There it is. And of course, you can put that in as a decimal. If you wanted to, oops, I didn't want to math frac that. 11 out of 221. It's about a 5% probability, right? So it's a 0.0497. So very close to 0.05. Okay, about a 5% chance of getting that. Okay. So 1 in 20 roughly, and that makes sense there. 11 out of 221 is pretty close to a 1 in 20 chance. Okay. Okay. So anyway, you can kind of see how the second face card, the probability of that second one coming up a face card is changed or altered by the first one being a face card. And if that first one wasn't a face card, then things are different. Now here's something interesting as well. The second one being a face card, if the first one was not a face card, that probability is changed as well. So let's say, for instance, I were to deal out a 2 of spade as my first card. Then I've removed one card, so there's 51 in the deck, but there's still 12 face cards. So the chances of getting, or the probability of getting a face card as a second card is not 11 out of 51, it would be 12 out of 51. Okay, so you really have to take into account both the numerator and denominator on how those counts change. Maybe both of them change like they did in this case, or maybe just one of them changes like the denominator in the case where you get a non-face card dealt first, followed by a face card. Okay, so it really depends upon the situation. You have to really think through these. There's not like a nice quick formula for it. It's all dependent upon the situation, how it's described. But in the end, you do have to multiply the two probabilities together.